Transporting a gigantic amount of information in the form of optical signals is undoubtedly one of the great technological revolutions of the 20th century. In just 1 second, every piece of information you send has the time to travel around the Earth 5 times. This achievement is possible at an energy cost 10 times lower than 4G, thanks to optical fiber. But at the end of the journey, to be read and processed by the electronic circuits of our phones and computers, this information must be converted into an electrical signal. This transformation, and then the processing of info, is very energy intensive, mostly wasted by heating of km of microwires within processors of our devices. The ideal scenario would be to directly harness the light signal coming from the fiber, but this is not yet possible. The DALHAI project aims to develop calculators or microprocessors, all optical, that will use light instead of electricity to process information 1,000 times faster and without component heating. The DALHAI microprocessors will directly perform calculations without requiring a multitude of interconnected electronic transistors. Decreasing the number of connections leads to space savings and a reduction in energy loss.
Hello, my name is Eric Dujardin. I'm a CNRS researcher and leader of the DALHAI project. Any piece of information, be it an image, a video, a text or a voice, is encoded as zeros and ones. Instead of using circuits with a multitude of transistors to process information, DALHAI will use a single but reconfigurable gold microplatelet. It gets information as ultra-short laser pulses and sends back the result as a light signal. The shape of the platelet and the laser characteristics define the type of computation it realizes. Our first prototype is a hexagonal gold cavity with only 60 nanometer thick, 2500 nanometer long, and 1500 nanometer wide. We combine chemistry of ultra-thin gold crystals with the most precise nanofabrication techniques.
Now, here are the new crystalline gold platelets. How do we make them?
I directly grow them on glass substrate. The substrates are immersed in a solution containing gold mica salt, and they are heated at 80 degrees centigrade for several days. I modulate their conditions to keep them ultra thin, and the glass substrates are actually helpful to keep them flattened.
Okay, so we can see with this electron microscope that they're very large. What are their sizes?
Yes, I have exceeded 150 microns while keeping them as thin as possible within the range of 80 nanometer. So they are around 2,000 times thinner than white.
The new platelets are large enough for 1,000 logic gate devices on each, but how should we nanofabricate them?
I can use these crystalline flakes into a focus ion beam microscope. The very sharp ion beam will sculpt and remove the gold atoms we don't need, and then we can make any shape we want. And the microscope has a nanometric resolution, and also it preserves the crystallinity of the structure.
Yeah, but focused ion beam will make them one by one. Perhaps we have to find another strategy to make them parallel.
So I can create all these patterns using electron lithography at once?
Yeah, and then we can use in parallel ion beam to test many different shapes at once.
Once fabricated, the cavity is placed on an inverted optical microscope. For now, 2 laser beams are focused on it, but we plan to expand to 4, 8, and then 16 beams. Alexandre Bouelier, our optical physicist expert, explains how challenging this is.
Indeed, to drive our prototype, an ultra-short laser pulse is split in 2 beams. We control their polarization state and focus them on 2 preset inputs of the device. But we already developed a 4-beam strategy with a second microscope objective. Yet, this upgrade will not allow us to drive n inputs simultaneously while controlling all parameters required for the ALU processor. So we need to invent a new experimental approach to manage this complex operation in a single device while keeping the major assets of our optical approach, the incredible speed of optical signals and the prospect of merging those processors with other optical communication technologies.
The double hexagon concept is inspired from the electronic behavior of molecules. It can perform many Boolean operations and even add two simple numbers. I dream of achieving more sophisticated computation like a processor. But unlike microelectronics that followed the guidelines of Claude Shannon 80 years ago, we miss a formal framework to achieve complex computation. Therefore, DALHAI relies on experts like Gérard Collat-Desfrancs to predict the behavior of our cavities.
We model the optical signal produced by the platelets and the parameters for achieving functions such as comparing or adding two numbers. This work has two aspects. First, developing a physical model to describe the optical response of platelets for a given shape to explore their capability to realize one or more logical functions. And secondly, we test new forms realizing increasingly complex logical functions targeted a priori. A wide variety of shapes is possible, and for each one, there is a large number of combinations of excitations. It is therefore a direct but time-consuming method. Moreover, it relies on intuition to choose the shapes to test. This is why, in collaboration with the SIAD, we are trying to optimize the shapes through new approaches that combine reliable physics models and rapid estimation of the optical response by neural networks associated with an ontological approach.
Device simulation allows us to test ideas for devices without actually fabricating and measuring them. Yet, we wish to go beyond our intuition. We are creating a digital expert based on artificial intelligence that will propose an optical solution for a given Boolean calculation, including the cavity shape and the input-output configurations.
To design an AI solution that goes beyond the intuitions of business experts, we need to collect, structure, and formalize the knowledge and physical constraints that must be integrated into the machine learning process. To do this, we apply a collaborative knowledge elicitation approach to collect and select the business knowledge to be provided to the machine. This work is carried out in close collaboration with domain specialists and involves conducting interviews to acquire knowledge in order to build an ontological model capable of reasoning based on the analysis of experimental data and the expertise of the experts.
To design logic gates, two parts to optimize are geometric shapes and laser parameters. How do you perceive it?
Starting from initial characteristics and then optimizing performance, in my opinion, it's better to go with genetic algorithms.
And what is the working mechanism of it?
In Darwin mode, meaning that hundreds of specimens will be generated. For each, reactive values are assigned to the different initial characteristics. The quality of the logic gates obtained is evaluated for each of them. The best ones are kept, and they are made to reproduce again, so that their offspring are better than their parents. And this will be done for as many generations as necessary.
And the best ones are tested on the physicist's bench to verify their performance?
Perfectly.
Hybridizations combines various artificial algorithms. A genetic one that designs shapes whose complexity is analyzed by artificial deduction. A CNN evaluates these shapes for light scattering, and a second genetic algorithm optimizes logic gates for each scattering. The data is compiled in an ontology to explain the results to the user.
So far, our digital expert has suggested devices up to 3 times better performing than our initial double hexagon. These designs have already been nanofabricated and will be tested on Alexandre Bouhelier's microscope. In the meantime, the expert is looking for a 2x2 bed device requiring 4 laser beams, for which the test bed is being built. With this interplay between artificial intelligence and experiments, we are gradually improving our optical computers and will explore the limit of this innovation.
With DALHAI, the world of photonics has initiated its miniaturization to meet the challenge of optical information processing. At this scale, 1,000,000 times smaller than a meter, our machines will compute at the speed of light,